thank you very much, Bea and Julie, for the invitation. It's a great moment to share all together, although of course remotely, but next time hopefully it will be in real presence. I'll be happy to talk about haptics right now. So how haptics can improve subjective experience in virtual reality. It's basically a presentation of the results and the research activity, a part of the research activity of my team at Inria in Rennes, in the far west of France, on the west part of France, here highlighted in purple in the French map. And it's a group of something like 35 people who are dedicated to virtual reality, and more specifically to the design and evaluation and assessment of VR technologies. So we are a computer science lab. We are not a neuroscience lab or a perception or psychology lab. Our main objective is really to design and foster the transfer of virtual reality technologies in the society, virtual or augmented reality technologies. Here is an example of the nice setup we have in Rennes. The nice setups we have in Rennes. This is the Immersia room. It's a big, it's a very large cave environment, so a bit different from the HMDs, the head-mounted display. Here you are fully immersed in a virtual environment by means of a projection-based display, those big screens surrounding you. And it's quite different in terms of sensation of immersion, because here you see your own body, you continue to see your own body, and possibly the other users also together with you, the real users embedded with you inside this cave environment. But the immersion sensation is very powerful also in this cave system. And if you haven't tried them yet, it's a good occasion to come and visit in Brittany for testing these impressive setups. And recently, the second video at the bottom of the slide is showing our integration of haptic interfaces inside this cave environment. We have force feedback devices like this one that you're seeing here on this video here. This large force feedback device, which is enabling to interact physically with the virtual content by means of haptic technologies. So the research path in our group is to design and study the application of VR technologies in the society, but actually there is a close link with perception, with psychology and neuroscience. We like to consider those fields as a main source of inspiration for the design of our technologies. It's also a main source of criteria for evaluating our technologies. And as a secondary goal, we often like to exploit our technologies to investigate human perception, human behavior, human psychology in virtual worlds. We are deeply concerned by the implication of those technology on human perception, and we are fascinated by the potential use of this technology as an experimental paradigm for studying the brain and the perceptual mechanisms, for instance. So a lot of our works are actually strongly connected with colleagues from neuroscience or psychology, and we like to study also the human perception and psychology in virtual worlds. Another characteristic of our approach is we like to design hybrid systems, in the sense that we like to combine and increase the level of complexity by mixing different technologies together. And we are lucky to have experts and skills in different kinds of technologies, including visual displays, haptics, but also brain-computer interfaces, gaze tracking, motion tracking, etc. And we like to also to study the convergence of all these technologies in more elaborated and sophisticated hybrid systems. Some examples of such kind of hybrid setup. This is a video of a rather recent connection between the augmented reality technology. It's a HoloLens, a Microsoft HoloLens video see-through system, which was for the first time connected with a brain-computer interface to see the feasibility and the design of specific interfaces for human-robot here interaction and human-robot control of a mobile robot by means of augmented reality and brain-computer interface. So here the user is controlling the motion of this mobile robot, going left, turning right, or advancing by focusing his attention on those flickering targets, which are, after that, evoking some potentials in the visual cortex at the bottom of the head. And by controlling your attention on those flickering targets, you can launch some commands and make this robot move in the real world by focusing your attention on those different targets. Another representative example of those hybrid setups is this also first and quite pioneering setup in 2012, where we combine, I think it was for the first time, a force feedback device and a brain-computer interface together in real time in this quite unique setup where you extract the mental workload of the user. If the workload is, it's basically only two classes, and it's a rather simple setup in terms of EEG processing, but it's extracting a high or low mental workload. And depending on this mental workload level, high or low, we activate a haptic guidance system. So here the user has to pass through the maze here. And when it's difficult, we activate a guidance, a force feedback, which is somehow helping the user by repulsing from the walls and generating a sliding effect, haptic sliding effect, for going more easily into this 2D maze. And it was a really nice hybrid system showing the compatibility of real-time EEG extraction and brain-computer interface and force feedback device. Voilà. And to illustrate also this other intention from our group, to exploit our technologies and VR to study also brain mechanisms. Here it's a very interesting work that we conducted with Camille Genet, psychologist, on studying the neurophysiological markers of immersion and the different kinds of illusions that Mel talked about at the beginning of this day in VR, especially here trying to identify neurophysiological markers of agency and control of your virtual body, or virtual embodiment and body ownership, especially agency here. And interestingly, in this work, we could identify some brain pattern here and brain activity, which are elicited when you lose the control of your virtual body. So it's quite similar to other works that I think, Mavi, you were involved in which you find, for instance, error potential in the brain at this moment where you lose the control of your virtual body. And here in our example, we also could identify error potential, but when you lose the control of these virtual hand movements, which are artifacted, and you have, for instance, a wrong virtual finger, which is moving when you are moving your real finger. But in this case, we also found some really nice activation of some brain areas, which actually corresponds to the activations that are noticed in the brain of schizophrenic patients when they are experiencing an hallucination, a sensory hallucination. So it was quite interesting to find this equivalency between what you feel and what your brain is experiencing in VR in case of losing the control of your virtual body, and those hallucination brain patterns that are observed in schizophrenic patients. Okay, let's enter the topic of haptic technologies now. It's a long story at Inria Rennes. We have been engaged in this design of haptic technologies for more than 20 years. It's really something that we are passionate of. We really like this kind of technologies for touching, entering in contact with virtual reality, feeling the matter and the virtual matter. It's a long story also in the field of VR, but it's still a very hot topic because it's very complex. It's a real challenge to try to propose compelling technologies which enable to make you feel very, very complete sensations when you enter in contact with virtual objects. So it's a very hot topic at the moment in the community, and there are lots of companies, labs, trying to elaborate haptic modules to equip the future VR equipments complementing the HMDs of the future. So it's a very exciting field of research at the moment, and there are lots of technological labs designing haptic technologies. And there are lots of new paths and sometimes old paths which are revisited today. I'm listing here lots of examples of those kind of haptic approaches which are currently investigated in the haptic community and also at Inria Rennes in our group and in the others at Inria Rennes. Because we are 3 teams at Inria Rennes working on this topic of haptics. So for instance, ground-based haptics, I'll show some examples, wearable haptics, encounter type haptics, mid-air haptics, surface haptics, passive haptics, etc., etc. I'll show some examples right now just to illustrate really the variety of the field and the richness of the field at the moment. So these are some examples from our group. This is, for instance, an example of wearable haptic system. It's a strip which is pressing and generating a contact sensation and a pressure sensation at the level of one of the phalanx of the finger, which is used in conjunction with a passive haptic system, a tangible device, which is here meant to simulate the body of a patient in a palpation, a medical palpation context. So here it's really illustrating this very current and trendy path in the haptic community regarding wearable haptics, haptics that you can wear and equip when you manipulate or enter in contact with the virtual world, especially with an HMD. Here it's a recent example of a work that we have conducted on the field of surface haptics, trying to increase the sensation you have when you interact with touch surfaces like smartphones or tablets. There are lots of works on this topic. Here is one example where we really interestingly combine surface haptics and interaction with surfaces with a ground-based haptic interface. So you have a force feedback device here, which is used to simulate a haptic sensation, kinesthetic sensation, force sensation when you interact with a tablet surface to make you feel here the texture of the image here. So the roughness, the relief, the viscosity, the resistance, or different tactile or haptic sensation you would have when experiencing the interaction with this image. So this is basically ground-based interface, but here to enhance interaction with a surface, so it's a surface haptics as well. A very trendy approach also at the moment is a mid-air haptics, so very unobtrusive haptic approach. Here it's an interface that we extended from Ultralip. It's an ultrasonic device which is sending remotely waves, ultrasonic waves, to make you feel, for instance, the shape of an object at the level of your hand without wearing any device. So that's one of the benefits of this approach. And here we have augmented this approach by adding motors in order to orient and change the orientation in 3 degrees of freedom of this platform to have a larger workspace here and making it possible to render 3D holograms and touching 3D holograms. And this is another approach which is quite trendy at the moment. It was a pretty old approach, dating from the 90s, but it's still revisited at the moment. Encounter type haptics. So here we're using robots. It could be drones, it can be mobile robots. Here it's a robotic arm, which is moving in order to anticipate your motion and activate contact when you are supposedly entering in contact with a virtual object. So here it's a painting application. So you have a large surface to paint. And actually you have a very small surface at the extremity of the robot, but it's moving to anticipate your movement and giving you the illusion that you are exploring a very large surface and painting over a very large surface, although you are actually interacting with a very small surface at the extremity of the robot. So this is called encounter type haptics. So the idea here was to show you really the variety of examples of actuation systems, haptic passes in the community at the moment. It's a very rich and very exciting technological field and very active technological field. But what is very interesting also in this topic is that it's not only about technology, it's also about perception and psychology and multisensory integration and fusion. And especially in the case of haptics and haptics in VR, we are looking for tricks, for perceptual tricks to blur the mind, to blur the brain and generate haptic sensation, because the task is so complex that we need to find some alternative solutions to generate compelling haptic sensation. So this is the case for pseudo-haptic feedback. It's something that I launched during my PhD 24 years ago, when actually I was working on haptics and haptic technologies, and my own force feedback device failed and had to be sent back to its company in the US. And I was, during my PhD, I was in charge of studying haptic rendering and haptic algorithms for force feedback device, but my force feedback was broken. So I had to find alternative ways of simulating haptic sensations without a haptic interface. And that was the beginning of pseudo-haptics, which is now a plain field of research in the haptic community. The idea is to exploit visual feedback and visual effects in reaction to your own actions in the environment to generate some kind of haptic sensation and haptic percepts. So this is one of the famous examples of this approach in the case of tactile images. And here the idea is to simulate the relief of the image, the bumps and holes in the image, the hollow on the left and the bump on the right. And a very basic technique that we are using here to simulate the sensation of falling into the hollow or climbing the bump. To do so, we simply change the motion of the cursor. We reduce artificially the speed of the cursor when decreasing the height of the image, and when increasing in the height of the image when climbing the bump, and we accelerate the cursor when we decrease over the heights of the image, and for instance here when we descend the bump. So these very basic techniques, just slowing down or accelerating the cursor, is working really well. It provides you some kind of haptic percept that we call pseudo-haptic sensation at the limit between visual and haptics. And the sensations are sometimes very comparable to haptic sensations, real haptic sensations and sensations that are provided by real haptics. So we have a long history of results if you are interested on pseudo-haptics and how it can be incorporated in virtual environments to increase the experience and the immersion of the user. Some examples here in these other slides. Of course, there are lots of examples, but I picked up only 4 of them. At the bottom left here, you see a work that we've carried out on pseudo-haptic avatars. And here we have an avatar, which is an avatar-based interaction for simulating weightlifting. And by using also pseudo-haptic tricks, we decrease the motion, for instance, of the dumbbell, and the weight sensation is increased. You have the impression that you have a very heavy dumbbell. And if you, on the contrary, you accelerate the motion that you are looking at in the mirror, then you have the impression that the virtual dumbbell is much lighter. And it's also very efficient. On the top right, it's another pseudo-haptic techniques to increase interaction with surfaces. Here we propose different deformations at the level of this virtual cursor here to simulate texture effects like relief, friction, or here texture. And then we could combine this haptic approach with different kind of input devices, like here this elastic input that we use in conjunction with pseudo-haptic effects to increase, for instance, the sensation of entering in contact and collisions with the different objects that are populating the scene here in this virtual cockpit, for instance. And we can combine pseudo-haptics with passive haptics and elastic inputs like this one. And we have shown that it's increasing a lot the immersion of the user and the sensations that you can get from this pseudo-haptic sensations in terms of stiffness here or contact information. And this was the same also for this passive exoskeleton. This was for generating various grasping sensation, the impression of grasping virtual objects, here again in a palpation scenario. And together with pseudo-haptics, we exploit this passive exoskeleton designed with Japanese colleagues at Tokyo Electrotech for generating fake and phantom grasping sensation. Okay. Another really nice illustration of this cross-modal approach in which we try to find other ways and alternative approach to exploit haptic input in human perception in virtual environment is this really nice work that we started with Alain Berthoz actually at Collège de France something like 10 years ago with Nizar Warti during his postdoc, and that we called this new paradigm that we call haptic motion. And here we studied how haptic and force feedback, in particular kinesthetic sensation, could be used as an input for self-motion perception. Can haptic be used as an entry point, as a stimulation process for increasing or generating self-motion sensation in virtual worlds, in virtual environments? And we did this pioneer experiment with Alain Berthoz, like something like 10 years ago with Nizar, where we exposed some participants to visual cues known to induce self-motion illusion and vection illusion. So I don't know if you are familiar with vection illusion, but it's the kind of illusion that you are facing in a train when you are entering a train and sitting on a seat, and the train just next to yours is starting, and you have the impression that it's your own train which has just started, and you are experiencing a self-motion illusion. You have the impression that your own body is perceiving this acceleration of the train starting. It's the vection illusion, the self-motion illusion. And interestingly here in this work, I'm launching the video, we expose some participants to visual cues which are known to elicit vection illusion. And at the same time, we exerted some force feedback here at the level of the hand. And we generated a force which is proportional to the visual acceleration. And very interestingly, we've shown and we found that in presence of this redundant sensory cue, this force proportional to visual acceleration, the frequency of occurrence of vection, the duration of vection illusion, and the onset of the vection illusions were higher. In other words, the presence of force feedback is increasing the self-motion perception. So later on, we after this really fundamental study and this fundamental discovery of this phenomenon, we could interestingly exploit this haptic motion illusion in a wide range of setups. For instance, with Interdigital company, we explored a completely new field of research called haptic cinematography, or how to increase the sensation and the immersion of users when watching movies by means of haptic motion, and trying to imagine the haptic seats, the seats of the future movie theaters. And we came up with this really great setup here called the Hapseat, in which the armchairs here or the headset are exerting forces on the body, forces that are proportional to the visual acceleration that is displayed in the movie, in the video, or in the game. I'm trying to launch the video again. Let me do that. Yeah, right now. So you see here the armrests here and the headset are exerting forces on the body, which are exactly proportional to the acceleration which was measured by an IMU, by a motion tracking systems in this video here. And the sensations are very powerful. And what is very interesting here is that when compared to traditional setups and traditional systems in which the chair is moving, is actuated, like in 4D movie theaters, if you go to the Futuroscope in Poitiers, the entire chair is moving. And here what is interesting is that the chair is completely completely static. And only those elements are applying forces on the body, and the sensations are extremely important and extremely strong. So it's a completely new paradigm for 4D movies and haptic movie theaters. Later on, we also, that was one of the first and initial ideas of haptic motion. We applied this concept also to driving simulation in this, for instance, haptic augmented driving simulator. And the idea is to exert forces at the level of the wheel here. So it's a gamepad, but you can imagine that it's also working with a wheel. And you apply forces here at the level of the hands of the user, which are again proportional to the visual acceleration. And here also we found and we showed that the impression of the user, the immersion of the user was much stronger, and the self-motion sensations were much stronger in presence of this very simple and very basic force feedback addition. And this is our really latest work on the topic. It's unpublished work. We just did the archive a couple of months ago. It's probably one of the most impressive. It's a very sophisticated setup in which we directly try to propose haptic motion inside HMDs at the level of the head. So here we have a force feedback device, which is attached to the head of the user, equipped with the VR HMDs, in order to apply haptic motion sensations, again, proportional with the visual accelerations felt by the user. So it's quite a complex, and it was a very challenging setup, and it's quite impressive. You have to be very careful in terms of safety for the user. But here is the video, which again is unpublished, but I think you will understand the concept better with this video. And you see that the head of the user is actively moved by the system in order to mimic the acceleration which is felt during here this glider scenario. The system is super impressive. It's the sensations are quite strong. Our impression, but it's not. It's to be confirmed, is that it's reducing cyber sickness. It's strongly increasing the self-motion sensation. But future work is really needed on this topic. It's a very exciting topic of research. Okay, and to complete now and finish a bit this presentation with going back to this notion of body ownership, avatar, and virtual embodiment in VR, and the relation with haptics, as it has been already shown in the previous presentation, the role of sensory stimulation, multisensory stimulation is very important in body ownership illusion and virtual embodiment illusion. We also studied this topic, and it's very exciting for us to propose haptic cues which are dedicated to increase virtual embodiment and strengthen the virtual embodiment illusions in VR. And for instance, we wanted to study the importance of having a strong ecological cue, because a lot of haptic setups in VR are very symbolic and very basic. It's most often and usually it's a vibrotactile feedback. It's a vibration which is provided to the user in the handle of or in the gamepad. And we wanted to see the interest of adding more sophisticated haptics in virtual embodiment illusions. So here in this example, we proposed a task, a 3D task, which was a drawing task. I'll activate the video here. It was a drawing task. You have to paint a mandala in VR. And you have a realistic avatar. And we are going to study the body ownership illusion and the virtual embodiment illusion toward this avatar in VR in different conditions, without any haptics, with very symbolic haptics, the classic ones that you have in VR, vibration, which is activated when you touch the mandala. So you just have a vibration. It's not a realistic haptic use, but it's an augmentation, a sensory augmentation of the immersion, and a physical force feedback, which corresponds to a real contact with the sheet here. So a blocking of your hand and read the sensation of touching an object. And we indeed found that the closest the haptic feedback to the ecological situation, meaning if you have a real force feedback here, the body ownership, the virtual embodiment was higher than if you have only a vibratory feedback and compared to also the visual feedback. So this promotes the use of ecological haptics in virtual embodiment studies. And to finish with and provide a closing with a very teasing and fascinating work that we explored also in VR. Is, as Mavi said, it's really interesting to study in VR non-realistic or surrealistic situations. And we also wanted to study how to push further the embodiment illusions. And here we wanted to see if you could feel embodiment toward a body which has a very different morphology. And that's why we studied this, we proposed this nice experimental paradigm called the six-finger illusion. Let me launch the video again, if it works. Let's see, yeah. Voila. So you have this virtual hand, this virtual body, which is very similar to yours, but actually at the level of your hand, there is an extra finger. There is a sixth finger located here, just before the pinky finger. And we add a very basic motion simulation where the motion of this additional finger is just extrapolated when taking into account the two surrounding fingers for moving this finger. Of course, it could be interesting to use BCI, as Mavi said earlier, to control this body, for this extra limb, for instance. But what is more interesting even is that we really wanted to make the participant feel this extra finger. And to do so, we adapted the rubber hand illusion paradigm in order to make you feel this extra finger and this sixth finger. So we use this brush, this real brush, to make a real caress on the different fingers. And when in the simulation, the virtual brush is passing over the sixth finger, the real experimenter with the real brush is caressing again the ring finger, but in a very well synchronized manner, so that you really feel a strong sensation, the caress sensation in a very synchronized way with the visual feedback of the virtual brush brushing the extra and the sixth finger. And this setup is extremely well working. It's quite impressive. After a few minutes of caressing your sixth finger, you really start to feel this extra finger, and it's very powerful. And it's a nice example on how haptics and synchronized haptics and visual and cross-modal effects can be used to increase this experience in VR and those illusions in VR. Voila, this concludes my talk a little bit in advance, but it's good because I think everybody's exhausted and we have some time now for questions, I hope.
Thanks very much. Thanks very, very much. This is almost breathtaking.